Welcome back. All right, so welcome back. We are now beginning our first lightning round session. In this lightning round, we are going back to the basics on 6 topics prevalent in the CEDAR sessions. All questions will be asked via Slido, and the questions will be answered during the 15-minute Q&A panel at the end of the lightning round. Please upvote your favorite questions for each speaker. All questions not answered today will be answered in the student newsletter. And our first talk is on the long-term variability in the Ionosphere-Thermosphere-Mesosphere system, given by Dr. Federico Gasperini. Dr. Federico Gasperini is a research scientist at Orion Space Solutions in Louisville, Colorado. He received his PhD from the University of Colorado in December 2016, was a postdoctoral fellow at Utah State University in 2017, and ASP postdoctoral fellow at NCAR HAO from 2018 to 2020. Before joining Orion in August 2020, his research interests include the upper atmosphere environments of Earth and Mars, dynamical coupling between the lower and upper atmosphere and ionosphere via large-scale atmospheric waves, the effects of global change, meteorological disturbances, and space weather on the upper atmosphere, the utilization of space-borne in situ and remote sensing data and numerical models to elucidate ionosphere-thermosphere variability. Let's welcome Dr. Gasperini.
Thank you very much for this introduction, Megan. I would like to start by thanking the organizers for this opportunity. And in this talk, I will provide some details on long-term variability in the Ionosphere-Thermosphere-Mesosphere as associated with upper propagating waves. Let's see. Don't seem to be able to change the slide. Oh, here. Okay, so this is the outline of the presentation. I will provide a brief introduction into long-term variability in the ITM. And for this talk, I will define as long-term as variability that has timescales greater than 10 days or so. And then I will describe different modes of long-term variability in the ITM, that is the quasi-biennial oscillation, or QBO, the El Niño Southern Oscillation, or ENSO, solar cycle variations, as well as modes of intra-annual and intra-seasonal variability, such as the annual and semi-annual oscillation, AO and SAO, as well as the Madden-Julian oscillation, or MJO. So it is well known that most of the day-to-day and longitude variability in the ITM that is not associated with solar and geomagnetic effects is due to upper propagating waves, and these have different spatial and temporal scales. And later this morning, you'll hear a lot more details about some of these waves, but those include tides, Kelvin waves, planetary waves, as well as gravity waves that have different spatial and temporal scales. I would say that it's very important that we understand the ITM system so that we can improve our prediction capabilities. And long-term variability is one of those effects that perhaps can be better modeled. And there is a great review by Sassi et al. 2019 that describes the importance of long-term variability in the ITM, as well as the different processes that affect that. So this depiction here is from shows in the y-axis the approximate altitude and the of different processes and their characteristic timescale. It's a very complex system with sources of variability in the troposphere and stratosphere, such as the QBO and SAO. There is multiple different pathways to which this variability can be imparted into the upper atmosphere. But there are significant challenges in the way that we are able to understand how these variations are being imparted into the upper atmosphere, such as the way the waves are being filtered in the propagation, or they're being modulated by their sources. So in this talk, I will describe in more detail the QBO, ENSO, the El Niño Southern Oscillation, the solar cycle effects on waves, as well as modes of annual variability, which include the SAO, AO, and MJO. So the next slide will show the QBO. Let's see if I can switch here. So the QBO is an alternating westerly and easterly zonal wind regime that descends from the tropical troposphere, tropopause really, into rather the tropical upper stratosphere into the tropical tropopause. And you can see in this figure from Anstey and Shepard, 2014, this alternating wind regime that has approximately a 28-month cycle. It is the largest source of interannual variability in the tropical stratosphere, but its effects really propagate upwards. In fact, it is present, this variation in the mesosphere. It tends to have tends to be antiphase or with the stratosphere QBO, but it's not effective at propagating all the way up to the higher altitudes. But what it can do is that it can modulate waves, different spatial temporal scales, and so impart essentially the variability from below all the way up to the upper regions of the atmosphere and ionosphere. Now, the QBO ITM connections are not well established, partly because we have limited observations, and partly because the lower boundary forcing of some of the models they're unrealistic, and they use physical parameterizations, such as gravity wave drag. Also, there is aliasing from 26 to 28-month variations in the solar ultraviolet and UV, extreme ultraviolet, that make it hard for us to decouple effects coming from below from the ones in situ. And also there is complexity in the solar cycle QBO and ENSO coupling. The next slide will show will describe in some detail the El Niño Southern Oscillations effect in the ITM. And in particular, this is an irregular, as probably many of you are familiar, periodic variation in winds and sea surface temperatures in the tropical Eastern Pacific Ocean, wherein the warming phase is called El Niño, and the cooling phase is La Niña. And effects in the ITM have been presented by a number of studies. For example, work was done by Pedatella and Liu in 2012 and 2013 through numerical simulation that indicated ENSO-induced variability in the mesosphere lower thermosphere region, MLT, upwards of 10 to 30%, and ionospheric variability of 10 to 15%. This is a figure from Pedatella and Liu 2013, and it shows the zonal mean, zonal wind anomalies during January associated with El Niño. And here in panel A, we have EP flux divergence. Panel B shows meridional and vertical advection. In C, gravity waves, and this is the combined effect. But one of the findings from this study is that the diurnal westward one tide that you'll probably hear a lot more in the next talk is increased during El Niño, primarily due to enhanced tropospheric radiative forcing. And this study also showed numerically that the D3 and D2 non-migrating tides are primarily enhanced during La Niña, with a little response during El Niño, due primarily to the enhanced tropospheric latent heating. But effects combined effects between ENSO, the QBO, and the solar cycle and other effects are still aspects of current research. Now, the next slide will show effects associated with the solar cycle. We know that the solar cycle has important impacts into different waves in the ITM. There was done, a lot of researchers showed this, but work by Oberheide and al. 2009 examined solar cycle effects specifically in different tidal components and fields in the ITM. There was also work done on NO and CO2 radiative cooling, and work done by Jones et al. 2016 showed the impact of tides in different solar cycle conditions. And here, this dash curve here shows solar max conditions, and solar min is dotted as a function of altitude, and essentially showed that we have important modulation in composition associated with solar cycle, with very important effects also in the ionosphere, upwards of 20%. Myself and others have also looked observationally at the effect of solar cycle into the propagation of waves, and showed, for example, reduced amplitudes in some of the waves propagating from below in the middle thermosphere for increased solar activity. Here you see the DE3, that's a tide that tends to be primarily propagating from below. And in Saber and Goche data, and you see these effects. The next slide will just give a very quick overview on the AO and SAO. In particular, I'd like to point out here that the SAO shows up as maxima around the solstices and minima around the equinoxes. And this effect has been explained by different theories, but the recent work by Jones et al. Has really demonstrated numerically the importance of the thermospheric spoon mechanism. There is essentially a summer to winter circulation that causes stronger mixing in the thermosphere during solstices. But there are other effects, like the KZZ hypothesis by Sean and others, that are actually affecting the SAO. And so part of the work is, I think, still understanding what the relative contribution of different effects is and how that changes with latitude and local time, for example. So the next slide will just describe in a few details one of the sources of intraseasonal variability, that is the MJO. This is a very prominent source of intraseasonal variability in the tropical troposphere. And it was shown by Kumari et al. In 2020 and 2021, the effects on tides, in particular 25% variation in some of the non-migrating tides. We also showed the impact on some of the other waves all the way up to the thermosphere. And also the effects has been demonstrated on gravity waves, and also extending at higher latitudes than just the tropics. But the impacts on the ionosphere is still something that needs to be investigated, and for this we really need to be using both models and observations. The next slide will be the last, and it just provides a summary, in particular of the importance on the upper propagating waves that you'll hear a lot this morning about. And specifically in this case for coupling long-term variability from the lower atmosphere into the upper atmosphere. And the way that occurs can be through waves that are being modulated in the lower and middle atmosphere through their sources, as well as variable propagation conditions, as well as nonlinear interactions. It is critical in general that we improve our ability to model this variability in the thermosphere and hence the ionosphere. data from the Icon and Gold missions will do provide important data for this investigation. But in general, the ITM has a poor observational record. We need data to validate models. And the upcoming GDC, Geospace Dynamic Constellation, that will launch hopefully in the 5-year time frame, will provide very well-needed observations. Also, we would hope that the dynamic mission will receive attention and will be successful. And that would be provide very targeted observations on the height of, that would be enabling us to have understanding of the height evolution of the wave spectrum in the thermosphere. With that, I just leave it a couple of questions that I think are very important that are related to the physical mechanisms to which long-term variability is coupled from the lower and middle ITM into the upper atmosphere and their relative importance, as well as the impact of waves on the long-term trends of the ITM, which are questions that I think will need to be addressed in the upcoming years. With that, I'd like to thank you, and I'll take probably questions later this morning. So questions later.
Thank you, Dr. Gasperini. Next, we have Dr. McArthur Jones talking about planetary waves and tides. Dr. McArthur Jones, Mac, has devoted the last 9 years to developing an understanding of how synoptic scale waves of lower atmospheric origin impact the dynamics, thermodynamics, and chemistry of the ionosphere-thermosphere system, using both models and observations. Now, as a research physicist at the U.S. Naval Research Laboratory, Dr. Jones is continuing his research with the thermospheric general circulation models, TGCMs, to investigate how external and internal drivers affect the climate and variability of Earth's upper atmosphere. Dr. Jones also supports the development of naval upper atmospheric modeling, including the impending update of the NRL mass spectrometer incoherent scatter extended model. Dr. Jones is the father of 3 kids, and in his free time enjoys playing with them. And when he gets a little bit of free time, may sneak out for a round of golf or 2. Let's welcome Dr. Jones.
So, good morning, everyone. So I guess I should say first, happy Father's Day to all the fathers and single parents. Happy Juneteenth to everybody. It's an important day today, and also happy Pride Month. I think I've checked every one of the boxes, but I'm not sure. So, at any rate, as is the case with any of these sort of lightning and back to basics talks, you can imagine we could teach classes or whole semesters worth of material, but we're going to try to cram it into 15 minutes. And as such, I'm going to talk about 2 specific parts of the wave spectrum as in planetary waves and tides. So an example of all the different waves that would sort of fall into the planetary wave and tide part of the spectrum is shown here from a review article by Hanley Liu in 2016. And you'll notice there's solar tides, there's lunar tides, there's Rossby gravity waves, there's mixed Rossby gravity waves. But today I'm going to focus just on 2 of them, and I'm going to focus on mainly the wait for it. All right, whatever. Hey! Okay, I'm going to focus on those 2 parts of the spectrum, okay? Tides and planetary waves both have similar spatial scales, thousands to 10,000 kilometers. But really what separates them is their periods. Solar tides specifically, solar thermal tides, are subharmonics of the solar day, so 12, 24, 8-hour periods, whereas planetary waves have periods that are longer than a day and really extending from 2 to 20 days. And today, for the planetary wave spectrum, I'm going to focus mainly on the Rossby gravity waves, or what we refer to as normal modes. If you're interested in any of these other parts of the spectrum, whether it be lunar tides, whether it be Kelvin waves, I have some extra slides that, if they're distributed, please check them out. There's a lot of references there and review articles for everybody to check out. Okay. So, in words, simply, atmospheric thermal tides or solar thermal tides are global scale perturbations in wind, temperature, pressure, density that are subharmonics of a solar day and that are forced either through the daily cyclic absorption of solar radiation in Earth's atmosphere or other planetary atmospheres, and in Earth specifically, the latent heat release associated with deep tropical convection in the troposphere. So this is a schematic. What I'm showing here is sort of a simple schematic of what you would see if you were sort of a space-based observer. So that's the other important point, is how you interpret a wave's longitudinal variability or its wave number depends on whether or not you're looking up at it from the ground, say from like a radar, or whether or not you're looking at it from space for like a satellite. And so what you see here, if you were a space-based observer, which is what this is supposed to represent, you would see sort of a bulge of solar heating, right, that is represented here by the white part of the Earth, and obviously the dark side of the Earth. And what that bulge looks like is it looks like it's fixed respect to the sun, right, and the planet's rotating underneath it. So it's sort of in a local time perspective what you would see if you were standing, or if you can imagine our typical picture is we see the sun during the day, it goes away at night. And so then you can represent the heating rate as a function of a mean represented by this Q, and then sort of a linear superposition of different waves that have a frequency, which would here in our case would be N, which would represent sort of a subharmonic of a solar day, which would be diurnal, semi-diurnal, et cetera. And then you would have its variation as a function of other things, right? Because this heating varies as a function of latitude, longitude, height, time. Okay, so if we take that simple local time view of things, right, and we convert it to universal time, you see now we have this full equation, which is a lot of times what you'll see in literature, where you have this cosine wave, where you have n omega. Omega is the rotation rate of the Earth. T is universal time. You also see there's an n next to the lambda, which is longitude. And then you have a phase term, right? And so if we were to look at the phase, if we wanted to determine what the phase speed of an actual wave was for this particular simplified case, you would differentiate with respect to longitude, and you'd come out with negative omega, which is the negative rotation rate of the Earth. So that would tell us, for this sort of simplified view, okay, so to an observer from space, the bulge is fixed with respect to the sun, right, and the planet's rotating underneath it. That's our picture. Let me just do them all. There we go. So an observer on the ground, right, it looks like that bulge is moving westward with the apparent motion of the sun. So it looks like it's moving across the sky the same phase speed as the sun, right? And so this is why you would get something like a thermal tide, right, that propagates up from the lower atmosphere and then dissipated in the upper atmosphere. Okay, let's look at an animation of this, if this will work. Got it, okay. Well, look, now it's all going at once. Perfect. So what this is an example of a migrating diurnal tide picture as a function of longitude on the top and local time on the bottom, right? I'm like afraid to do anything. Wait. Okay. Okay. So you have two dots there, right? You have a red dot and a yellow dot. And this is, you could think of these as two observers fixed to the ground looking up, right? Think about them as like a radar system, and they're separated by 30 degrees in longitude, or about 2 hours in local time, right? So what you would see, that wasn't me. There we go, okay. So what you would see is, as the wave, as the sun basically moves across the sky, you'll notice that these observers see see a diurnal variation, right, as a function of local time. Well, what you notice is both observers see the same phase of the wave, right? Meaning that the tide is migrating across the sky, right? So that's one important characteristics of the migrating tides, is that they have the same phase at all longitudes, right? But that's sort of a simplified picture, right? That's assuming we have the same solar heating at all longitudes. But we know that that's not true, right? So what does it actually look like for a realistic, solar picture, which is it varies as spatially and altitudinally, right? There we go. All right, so now if if we have a spectrum, we generate a spectrum of waves when we consider the fact that the solar heating varies with longitude, right? And you get this top equation here, which is you have A for the amplitude of the wave. Again, N is your subharmonic of a solar day, 1, 2, 3, et cetera. You have S, which is your zonal wave number now. And of course, you have your phase term. Now, if we do the same differentiation that we did before, what you'll notice is that the zonal phase speed gives you an N over S term, right? So what does that tell us? It tells us a couple of things. It tells us if N is equal to S, that we still end up with the rotation rate of the Earth, which means the wave's migrating. But if N and S are not the same, which means you have, say, a 24-hour perturbation and a wave number in 3 or 4 in longitude, they're going to have a different phase speed than the apparent propagation of the sun, right? So you substitute back in for local time, that sort of pops out right down at the bottom where you end up with a longitude variation that's S minus N, right? So what does this tell us? At any given longitude, we have the sum of waves that define the local time pattern, right, of heating. And it's the same as before, but now this local time pattern in heating changes with longitude. And it also tells us that at any given local time, there's a sum of waves that describe the longitude dependence in heating, right? So let's look at an animation of that. So this is now one of the tides you'll probably hear a lot about this week. It's referred to as DE3 for short, or the diurnal eastward propagating tide with zonal wave number 3, right? So you see the 3 peaks as a function of longitude, but now let's take a look at these same, what the observers would see on the ground looking up. So if you notice that from ground-based observers, right, at different local times, you notice you're seeing different phases of the wave, right? So what does that tell us? It's a very important point, right? If it's a migrating tide, they see the same phase. If they're not migrating, or they're non-migrating as they're referred to, they see different phases of the wave, right? The other important point to take away from this is that if you were a ground-based observer, you wouldn't be able to separate the different waves because all you would see is this sort of diurnal variation, right? So this is why you need both longitude and local time coverage to be able to determine what wave is actually driving any sort of features in the mesosphere, thermosphere, and ionosphere. Okay, apparently they're all number 1, that's good. So here's an example of all the different things that you might hear about this week, the tides impact in the middle and upper atmosphere, right? And I want to give you sort of an example of one that's pretty common and has been discussed a lot over the last 10 to 15 years, and that's the idea that the tides modulate the E region wind dynamo and drive longitudinal variability in the F region or topside ionosphere, right? So an example here is shown, so on the, I guess, be the right-hand part of the slide, you see 2 plots as a function of longitude and altitude from 2 instruments on board the time satellite. Right on the top is the temperature, and on the bottom is the zonal wind. And what you'll notice is each one of those white X's sort of represents a peak or trough in the wave, as observed by these different instruments at a constant local time, right? And you can see these are sort of it shows you sort of a wave 4 picture in longitude, right? Well, it's also important that this is occurring in sort of in the E region, right, in the E region ionosphere. And when we're in the E region, we still have enough collisions between ions and neutrals that the neutral winds can move ions across magnetic field lines and set up an electric field, right, because the electrons will stay fixed to the magnetic field line. And so what that allows to do is it allows the plasma to E cross B drift vertically at the magnetic equator, right? Once we get up high enough, we have diffusion, we have gravity that pulls this plasma back down the field lines, and it creates something like a wave 4 distribution in the F region ionosphere. And sort of that's what we see here. And this has been, as you can see, I've referenced these different pictures, this has been observed by a number of different folks. And so this is an example from the CHAMP satellite observing the electron density at a constant local time. And what you'll notice is this crest to trough ratio, which is a measure of sort of the strength of the equatorial ionization anomaly. You'll notice that there's a wave 4 peak there. So you can see a direct influence of how waves generated in the lower atmosphere affect the F region ionosphere. So I'll just quickly try to do this because I know I'm getting bogged down for time here. The other thing I want to talk about was planetary waves, right? And planetary waves take a wide breadth, and the way we think about planetary waves is generally a synoptic scale weather map, right? Flow in a jet stream, that gets set up due to just the geography of Earth, right? But in the upper atmosphere, there's a specific set of planetary waves called Rossby normal modes that are kind of cool, and they're force-free solutions to our primitive equations with some assumptions. And so with these assumptions, the theory of these normal modes are predicted to be 2, 5, 8, and 12 days. But in reality, we see them at 2, 5, 10, and 16 days in the upper atmosphere. So the question is to why, and I kind of I show you an example there of some radar wind observations that show these peaks in meteor radar winds in the northern mid-latitudes. All right, so the idea here is that these normal modes are solutions to Laplace's tidal equation when we assume that the temperature doesn't change, there's no wind, and there's no dissipation. That's not really what happens, right? So if we actually have those different things, which we do on Earth, right? We have mean winds, we have temperature changes and temperature gradients, and we have dissipation, that you get shifts in these wave frequencies that are predicted by classical theory, right? And so a lot of this work was done by Salby in the late 1970s and early 1980s, where he used a numerical model to show, okay, well, what if I relax some of these assumptions? What should I expect to see sort of in the middle atmosphere? And so I show an example of that on the right that shows you get these peaks this is the wind field, and this is the S equal 1. So this is a zonal wave number 1. But you get peaks around 5, 9, and about 15 days, which is close to what we actually see in the upper atmosphere. And so it led folks to conclude that these are actually normal mode oscillations in our atmosphere that occur just if you have any sort of forcing near these wave periods. And so we actually see that in the upper atmosphere. So I'll click through this quickly. But this is a recent paper, a 2019 paper, that looked at observations from that same SABRE instrument, showing up in the upper right-hand part of the slide a quasi 16-day wave, right, in temperature at this particular longitude and at about 40 north, and then corresponding changes in the F region ionosphere from the GOLD instrument, where we see 16-day wave oscillations. So it's just an example to show that even in an atmosphere where you wouldn't have any forcing, you could still get waves, and we would expect to see those effects the entire way through the atmospheric column. All right, so that's all that I have. Thank you, everyone. If you have any questions, I'd be happy to answer them. And again, happy Father's Day, happy Juneteenth, happy Pride Month. After the remote worked, it was fine.
Thank you.
Yeah, no problem.
Thank you, Mac. That was wonderful. Next, we will have Dr. Corwin Wright, and he will talk about gravity waves and turbulence. Dr. Corwin Wright got his Doctor of Philosophy in Atmospheric Physics at Oxford in 2006. Since 2017, he was a Royal Society University Research Fellow at the University of Bath, primarily working on gravity wave measurements across the whole depth of the atmosphere using diverse observational data sets, but with diversions like reanalysis quality assessment, sudden stratospheric warmings, and exploiting novel satellite data. He also has a science highlight on Friday morning. Let's welcome Dr. Wright.
Hello, I'll just wait for there we go. Okay, that should be animating, but it's not, but let's ignore it. Okay, so I'm going to talk briefly about gravity waves. As with the other topics, it's actually quite a deep one, so I'm going to skim the surface rather than go very deep. I like to start talks about gravity waves with this animation here. So what you're going to see is data from 2 satellites over northern Australia in visible van data here. You see these wave fronts going across here, and then at night time you see them in the water band here going across. And these fronts here are gravity waves traveling out from a weather system over here. And you get these fairly ubiquitous through the atmosphere. These ones are particularly clear, but you do see them in a lot of places a lot of the time, and particularly as you go higher up in the atmosphere, features like this are available pretty much everywhere. And I'm having the same problem. You do get them from a range of scales though, and so for example here we have some waves visible in not-lucent cloud, probably scales of tens of kilometers over France. Here, there's some scales of probably, again, 10 to 100 kilometers over a lake in Canada, and these are some ones at a much larger scale over the eastern seaboard of the United States. So these waves occur at all scales and all heights throughout the atmosphere. You can go down to maybe 10 kilometers in the horizontal, maybe a bit lower. You can go to thousands in the vertical before you start to turn into Rossby waves. What they're not is they're not the gravitational waves from Einstein. They're a very different kind of physics, so they're not that. And because I have to find pieces of gravity waves a lot of the time, I also have to tell you they're not the gravity wave ride at fun fields, because when I Google pictures of gravity waves, this is what comes up every time. So it's not that. Okay, so now I'd like to talk a little bit about the physics of what's going on. So what causes these waves? Where do they come from? The one that you saw a minute ago, that is a convective wave. It's generated by heavy convection north of Australia. And that convection is sort of angry air bumping up and down. That kicks the waves off and they travel away from the storm. In the real atmosphere, that's probably the second most common source of gravity waves, particularly in the middle atmosphere. The biggest one is orographic waves, which just flow over mountains. And that is probably about 50 to 60% of the waves, maybe more. It's a hard number to pin down. These are the two dominant sources, the two big boys, but there are some smaller ones. The process of weather front generation, that can generate waves that kick off like this. Storms, so lightning can trigger them, more rarely. And then there's lots of internal processes in the atmospheric column as well, like wind shear, geostrophic adjustment, and there's a long tail of small sources of gravity waves. And these all have one thing in common, and that's a common physical mechanism. And the physical mechanism is essentially like this. So I'm going to show you an animation. This is time on the horizontal axis, and this is a single parcel of air, and it's starting at rest. And what we're going to do is we're going to kick that with a displacement force. That could be flow over a mountain, it could be the storm, any kind of displacement force. And if we start it running, and if we're in a stably stratified atmosphere, so we have height and density, which is true of most of the atmosphere, particularly the stratosphere and above, and then we kick it off with that displacement force, we get something like this. So this is a force diagram, and these are the forces acting. So that initial displacement pulls it up, and then it gets to the top, but then it's too heavy. And because it's heavy where it is, gravity pulls it down. But then in the same way when you're in a bath and you push a rubber duck down and it bounces, a buoyancy force starts to kick in. That buoyancy force eventually overpowers the gravity force, and then it bounces up again. But then the buoyancy force shrinks and shrinks, the gravity is constant, gravity pulls it down. And this is going on for a single parcel on the spot like this, and this is then kicking the parcels above, and you get a propagating waveform moving away from the origin of the displacement force. And this goes on in the horizontal and in the vertical. And the period of this can vary quite a lot. It depends strongly on latitude. The lower limit is mostly determined by the Brunt Messiah frequency, the buoyancy of the air. The upper limit is determined by the Coriolis parameter, so it's different at the equator to the poles. And with latitude, it's probably 10 to 14 hours is the upper limit. So how do these waves travel through the atmosphere once they're doing that? We've got a little mountain down here, a little storm down here, and then the different layers of the atmosphere that you're familiar with here. I should say I'm mostly a stratospheric scientist, so I think mostly in this region here, but you're obviously all up here. So first of all, the waves are generated from here, and they can just propagate away, and then they do that. Sometimes they just propagate into a part of the atmosphere, say somewhere around here, break down to turbulence. That turbulence causes other things to happen. However, they can also travel upwards and generate more waves by various processes that are quite poorly understood at the moment. And they can in turn generate more waves, and they can couple into the ionosphere as well, quite effectively. They can also interact with each other, and the physics of this is, again, the theory is reasonably clear, but actually observing this is quite challenging. But they can interact and produce waves of different harmonics. They can be generated from turbulence over in situ processes. They can be generated by magnetospheric processes and thermospheric processes, which can then kick them down, although that's energetically harder for them to propagate a long way. They can go all over the place from turbulence, and that was what I thought I'd want more, but I don't. Okay, so why do we care about them? The first one is they're a big source of turbulence. So if you fly a lot over sort of mountain ranges, you often find turbulence can be quite severe, particularly around the Rockies near Denver. And that's because gravity waves are breaking at about the tropopause, and that's causing the turbulence that you're experiencing there. This turbulence can happen at all heights. It's not just at the tropopause, but as you go further up, the gravity waves are less likely to be there. They can also help to generate clouds. This is particularly common in at the polar latitudes in winter. And that can happen at the tropopause and at the mesopause. And they can, and also, and this is the main reason I care about them, they can slow the mean wind. So if this is the wind, the gravity waves break, they slow down the wind. And this can again happen at lots of different atmospheric layers. This breaking process can then drive the large atmospheric circulation because the waves are ubiquitous. And for example, they play a fairly big role in the lower branch of the Dobson circulation, so that's pushing flow out from the equator, and an even bigger role in the upper branch of Dobson, so that's pushing from pole to pole. And then my final example, which is probably most relevant to you, is they can couple into the ionosphere and cause TIDs to propagate away from the point. I should say that I've drawn them all as little wiggles, but they are emphatically 3D phenomena. This is an example of a fairly large one over the Andes, observed with the AIRS instrument. And you can see these hot and cold phase fronts. So we've got temperature perturbations in the air. Red is hot, blue is cold. You can see they're all wrapped around each other. They're all great big 3D floppy things that are traveling away. In terms of the properties, I've got here a little bit of a wave packet. And you can describe them primarily in terms of the wavelength in each direction. So in this one, you can see I've got a horizontal wavelength lambda y, horizontal wavelength lambda x, a vertical wavelength lambda z. And you can also think of those in terms of wave numbers k, l, and m. They're just the inverse of the wavelengths. We can define the wave as having an amplitude, and that could be an amplitude in wind, it could be in temperature, it could be in density, it could be in pressure. Lots of covariant parameters going on there. They also have a phase speed. That's the speed at which the wave fronts propagate, and that phase speed is inherently tied to a temporal frequency. And then the last one I really think about, they have group velocity. That's the speed the whole packet moves around, as opposed to the phase speed, which is the speed of the fronts. These parameters control the propagation of the waves. I won't dwell too much on this slide, but the point I want to make is that there are fixed relationships between these different properties, and they can constrain the wave quite heavily, what we call polarization relations. And these properties then control the propagation. So the phase speed is the temporal period and the wave number, and then the group velocity is controlled by the derivative of that. And if you know these and you have no background wind, which is pretty unlikely, you can work out which direction the wave will travel in and how far. In practice, the wind will tend to distort that. These properties control atmospheric distractions as well. So if you go back to that initial animation, these are perturbations in cloud caused by perturbations of temperature, and these are perturbations in water vapor that are being probably imposed by the combination of the temperature and the pressure and density effects. And finally, these properties control where the wave has done the momentum. So this is a diagram here, this is the wave here, and as it refracts through the air, if the wind's changing, and it hits a level where the wind speed equals the phase speed of the wave, that wave can break and dump the momentum of the wave, and that's one of the main controls on the jet streams in the stratosphere and the mesosphere. And to give an example of how severe effect this is a figure from Garcia 2015, and this is the standard Wacker model. This is a reanalysis mirror, and this is the difference they hypothesized due to lack of gravity waves, so they're getting a massive 10 meters a second bias in the wind speeds. I think it's better now, but there's still a bias there. I think I've only got a couple more slides. No, I've got 3 more, I think, like 4. So this is just an example of how hard they are to simulate. So this is essentially the same model. This is the Era 5 eccentric model, running at about a 0.2 degree resolution. This is a special high resolution run of the same model, running at 1 kilometer resolution. And you can see the maps that you get look completely different. So the physics is very hard to simulate, and depending on how you scale your model, you're going to get very different model fields. These diagrams here show histograms of what's in those ones. Ignore the yellow, that's the satellite instrument. But the point is that one resolution of the model, the wavelengths look like this, another look like this. They're completely different. So it's really hard to simulate. You have to get everything set up exactly right. And in practice, many models can't resolve them anyway. So this is a model grid here. This wave, absolutely fine. You're going to resolve that. Loads of points on the model grid. But this one is going to be way too small. And that's not an abstract problem, because a client model is running a 100-kilometer grid. These waves might have a horizontal wavelength of 10 kilometers, so you're not going to do them. So you have to parameterize the effects of these small waves, and that's a large field of research on its own. But there's a bigger problem, and that's an even harder problem. Some of them are a bit of both. They're sort of half on the grid, half not, and they're really hard. So the modelers have to parameterize both these tiny ones and these big ones, but not absorb the effects of these ones that are resolved on the grid. So it's a very hard modeling problem. And finally, the observations, which is my area. So it's also an equally hard observational problem. So we might have a wave here that looks like this. And then we might be able to measure it in lots of ways. We can fly balloons and aircraft through it. We can look at it from a ground-based radar or LiDAR. We can look at it from space with satellites. And we think, that's loads of measurements. We can easily characterize it. We can see really well what's going on. And ideally, we'd love to do that. But it's really bloody hard. So let's take an example here with 3 different instruments. So what I've got here is South America again. And this is the scan track of the Hurdles instrument. And Hurdles is flying along like this, and these are the little temperature measurements it makes, scanning up and down, scanning up and down. Red is hotter than normal, blue is colder than normal. And, sorry, this is a little bit slow, but I've still got 2 minutes, so we're fine. I'm not going to get in trouble. I tried to work out how to speed this one up on the plane yesterday, but it turns out you have to regenerate to speed it up. But you can see here, you can see these wave fronts going through like this, red, blue, and this is what Hurdles is seeing off the wave. So it's seeing the wave quite well. And we think, okay, well, let's look at it in the balloons, let's look in the radars. So let's look at it in the balloons. So we've got a sun station here in the Falklands, which fires off balloons a couple of times a day. This is a single pass of Hurdles. What you're going to see is a week of the balloons, and the red and the purple and green are wind perturbations. And 2 problems here. Firstly, you're at the wrong height. Secondly, you're in the wrong place. And that is a problem, and even if you're in the same place, you wouldn't really see the same thing for reasons I'll come to in a second. You can also look at it in a radar, and there's a radar sat right here. And that radar also looking in the wrong place. And again, even if you have satellite measurements in this place, the resolution is going to be wrong. So what do I mean by that resolution issue being wrong? Oh, sorry, I missed that. My point there is that since the waves are highly intermittent, they're not there all the time, they're coming and going, and the intermittency is very, very large, and they're varying on a very short spatial scale. So there's no way that you can assume that the wave here is the same as the wave here, unless you know something about its physics. And as a result, you can almost never measure the same wave from two instruments. But the big problem is what we call observational filtering, and this is where I'm going to end the talk, because I've got a minute left. So if you have a wave here like this has a horizontal wave in that direction, and in that direction, and it has some vertical wave out of the page, don't worry about it. So this is its wavelength in that direction, this is its wavelength in that direction. And you might want to measure that, but if this is the resolution of your instrument, you ain't going to see that wave. It's all going to be averaged into one big blob. And that is a fundamental problem with almost all satellite instruments. They can't really see them clearly. Whereas the ground-based instruments, you've got the opposite problem. They're often too small. They'll see sort of the structure around here, and they won't see the big picture. So whereas with, for example, chemistry, you can often measure a concentration that's representative. With waves, you need to measure the phase fronts, and to measure the phase fronts, you need the right resolution. You don't want to be too big, you don't want to be too small. It has to be Goldilocks, which is not ideal. And as an example of that, this is a simple wave, and then if you take that wave, convolve it with Gaussian, and sample it weirdly, the wave's going backwards. So this might be what you saw in one instrument, this might be the sampling of another instrument, and they're not meaningful to compare. If you look at that, you're going to say that wave's going that way, when clearly it's going that way in reality. So it's a really, really hard problem, and that sampling is a killer. So there we are. That's where I want to finish with 7 seconds to go. So I'll leave those points up on the side and escape before Megan shouts at me.
Thank you, Dr. Wright. That was wonderful. Next, we have Dr. Yosuke Yamazaki presenting on atmospheric vertical coupling. Dr. Yosuke Yamazaki received his PhD in Earth and Planetary Sciences from Kyushu University in Japan in 2011. He is currently a senior researcher at Leibniz Institute of Atmospheric Physics in Germany. His research interests mainly focus on studying atmospheric vertical coupling and atmosphere-ionosphere coupling. Let's welcome Dr. Yamazaki virtually.
Hello, thank you for the introduction. I hope you can hear me well. So in this presentation, I'm going to talk about vertical coupling of the atmosphere. So since it's a broad subject, I'm going to focus on a certain aspect of the atmospheric vertical coupling. That is, I'm going to explain the connection between the ionosphere and the atmosphere below. So the Earth's atmosphere is composed of different layers. And as previous speakers explained, the atmosphere can support various types of waves, including gravity waves, tides, and planetary waves. These waves are mainly generated in the troposphere and stratosphere. The low them can propagate vertically upward into the upper atmosphere. The upper atmosphere consists not only of neutral particles that makes the thermosphere, but also plasma particles that makes the ionosphere. And in this presentation, I'm going to explain the mechanisms by which the ionosphere is affected by atmospheric waves that are coming from below. The ionospheric weather is highly variable, and it changes significantly from one day to the next. So this movie, showing to the right in the middle, is made of a daily snapshot of total electron content, or TEC, observed during September 2011 at the fixed universal time daily. Total electron content is a highly integrated quantity of the ionospheric plasma density, and we can see a lot of day-to-day variability here because of the day-to-day change in the energy input into the ionosphere. Here I highlight the three processes. The first one is direct energy input by solar radiation. Extreme ultraviolet, or EUV, and X-rays are absorbed directly in the ionosphere. So this can be the source of day-to-day variation. And besides, the part of energy is transferred from the sun to the Earth in the form of solar wind. So the solar wind drives the magnetosphere, and the magnetosphere is connected to the polar region of the ionosphere by magnetic field lines. So the ionosphere can be disturbed by solar wind disturbances. And I think that this process will be, the next speakers will expand more on this coupling process. And finally, solar radiation, part of solar radiation drives the terrestrial weather, which we experience every day. The atmospheric waves are also produced in this process, and as I mentioned, some of them can propagate vertically upward into the ionosphere. So in this presentation, I'm going to explain how these atmospheric waves affect the ionosphere. Especially, I'm going to focus on the ionospheric plasma density at middle and low latitudes. The behavior of ionospheric plasma density is described by continuity equations. The equation says that the change of the ionospheric plasma density is due to either production of plasmas, loss of plasmas, or plasma transport. For production and loss mechanisms, we consider ion chemistry. And for the plasma transport, electrodynamics is important. This is because ionospheric plasmas tend to move with the so-called E cross B drift. Here, E is electric field and B is magnetic field. So plasmas tend to move in the direction perpendicular to both electric field and magnetic field. So when electric field changes, plasma transport changes, and the plasma density can also change. Now we are going to ask how the ion chemistry and electrodynamics can be affected by atmospheric waves coming from below. We first look at ionospheric electrodynamics. Electrodynamics deals with electric fields, denoted by E, and electric currents, denoted by J. The ionospheric plasmas consist of electrons and positive ions, and they move around as they collide with the neutral particles. And when they collide with neutral particles, the motions of electrons and ions are slightly but systematically different. This is because of the large difference in their mass and volume, and as well as the difference in the electric charge. The difference in the motions of electrons and ions lead to electric currents, and the charge accumulation due to currents produce electric fields. A mathematical expression for ionospheric currents can be obtained by writing down the flow of electric charge due to the difference between ion and electron velocities. And these velocities can be derived from momentum equations for ions and electrons, which are not shown here. But doing so, we can obtain the expression called ionospheric Ohm's law. J equals sigma E plus U cross B. And it's called ionospheric Ohm's law because it's similar form as Ohm's law. That is, electric currents are proportional to conductivity and times driving force. It's very important to note here that for ionospheric electrodynamics, the main driving force is U cross B. U is neutral wind velocity, and B is the geomagnetic field. This process can be understood in analogy with a dynamo. So in a normal dynamo, you move electrically conducting material with velocity U across the magnetic field B to get electric currents. For ionospheric dynamo, the U corresponds to the neutral wind velocity and B corresponds to the Earth's magnetic field. So when the neutral wind velocity changes due to atmospheric waves from below, the electric fields and the currents changes accordingly which affects the ionospheric plasma density. Here is an observational example of the electrodynamic effects associated with atmospheric waves. In September 2019, there was a large-scale disturbance in the middle atmosphere, so-called sudden stratospheric warming. And the important point here is that the event was accompanied by an unusually strong planetary wave with a period about 5 to 6 days. So bottom left panel here shows a 5 to 6 day oscillation in the neutral wind in the lower thermosphere as observed by a ground-based meteor radar. We can see a 5 to 6 day oscillation. And during the same time, ESA's satellite mission SWARM detected 5 to 6 day oscillations in the ionospheric electric field and plasma density as presented in the right panels. So these observations can be understood as arising from the modulation of ionospheric dynamo by planetary wave with a period about 5 to 6 days in this case. So now we looked at the plasma transport part. Now we are going to look at the ion chemistry, which is also important for the ionospheric plasma density. Since the main part of the ionosphere is made of O+, we are going to see the production and loss mechanism of O+ in the ionosphere. The main production mechanism of O+ is by photoionization of atomic oxygen. That is, photon kicks out one of electrons from atomic oxygen, leaving out O+ and electron. This is the main production mechanism of O+. For the loss mechanism, the opposite of this could happen. That is a recombination of O+ and electron, but that goes only slowly, and that's not the main loss mechanism of O+ in the ionosphere. Instead, the main loss mechanism for the O+ involves multi-step recombination involving a molecular nitrogen. That is, O+ first react with molecular nitrogen N2, producing NO+, and NO+ is immediately destroyed by recombination with electron. So important takeaway from here is that more atomic oxygen leads to more plasma density, while more molecular nitrogen leads to less plasma density. So ionospheric plasma density tends to vary with the ratio of atomic oxygen density to the molecular nitrogen density, which is often referred to as O2-N2 ratio. So it's interesting to note that if the composition of the thermosphere changes, the ionospheric plasma density changes as well. Now our question is how the O2-N2 ratio changes in response to atmospheric waves from below. Here I present the TIGCM model simulation results for the O2-N2 ratio response to upward propagating tides. As we can see here, model predicts the overall reduction of O2-N2 ratio in the thermosphere in response to tidal forcing. This is because the atmospheric disturbances coming from below have a mixing effect on the thermosphere. So without mixing by atmospheric forcing, the relatively heavy molecular nitrogens sit in the bottom of the thermosphere, and lighter species like atomic oxygen dominates the upper part of the thermosphere. But after mixing by atmospheric waves, the composition of the thermosphere becomes more uniform with respect to height. So if we look at this process at a certain height, we see a relative increase of molecular nitrogen and relative decrease of atomic oxygen. therefore reduction of O to N2 ratio, therefore reduction of ionospheric plasma density. So to summarize what we have discussed, so there are two processes that can be important for ionospheric plasma density response to atmospheric waves. The first one was the modulation of ionospheric dynamo by atmospheric waves. That is neutral wind perturbations drive electric fields and currents, and that modulates the plasma transport by E cross B drift. The second one was the mixing of the thermosphere by atmospheric waves. That is the atmospheric waves have a mixing effect on the thermosphere, changing the composition of the thermosphere, leading the reduction of O to N2 ratio, leading to the reduction of ionospheric plasma density. In the real atmosphere, these mechanisms can operate simultaneously. So the ionospheric response to atmospheric wave forcing can be complex. So this is something we need to keep in mind when we are interpreting the ionospheric data. So this is just a summary of what we discussed. I hope that you have got any useful information about vertical coupling of the atmosphere. That's all from me for now. Thank you.
Thank you, Dr. Yamazaki. Next, we have Dr. Leslie Lamarche talking about high latitude and polar processes. Dr. Leslie Lamarche received a PhD in physics from the University of Alaska Fairbanks in 2017. Her research focuses primarily on plasma physics processes in the high latitude ionosphere. She is currently employed at SRI International, where she works on projects related to scintillation in trans-ionospheric signals. Mesoscale structures imaged with advanced modular incoherent scatter radars, and plasma instability physics and cross-scale coupling. She has also been involved in the community efforts pertaining to data and software stewardship and improving the reproducibility of scientific research. Dr. Lamarche will join us at the student lunch tomorrow. Let's welcome Dr. Lamarche.
Okay, so next slide. I can't change them myself, or can I? Okay, thank you. So I'm talking about the high latitude today, and when I say high latitude, just to put it in a little bit of context, this is a pretty common figure of all the complexities that happen in the atmosphere and ionosphere and magnetosphere and their interactions. But I'm going to be focusing on kind of this region, so the polar cap and high latitudes. And generally, I'm talking about the region with a magnetic latitude greater than roughly 60 degrees. What I'll get into later, you'll see that 60-degree number is certainly not a hard cutoff. The boundary and what exactly you consider high latitude certainly changes. But I also wanted to emphasize at this point that, unfortunately, this slide deck is probably a little bit northern hemisphere centric, but everything I'm talking about applies equally both at the northern high latitude region and the southern high latitude region. Okay, next slide. So this includes, this was touched on briefly in the last presentation, but the connection between the solar wind, magnetosphere, and ionosphere. I'll be trying to give you just a really brief introduction to what the major regions are and some of the phenomena you're likely to hear about during this meeting that occur in these regions. Any one of these topics is very complex and very detailed, and could be people base their entire careers on them, but hopefully this talk will kind of at least introduce you to some of the things you might hear about in this meeting. So next slide. The solar terrestrial environment is what we call basically from the sun to the earth. So if the sun is way over there, you have the solar wind, which is both particles emitted by the sun as well as the interplanetary magnetic field, IMF. And that, when it reaches the earth, interacts with the earth's magnetosphere. So the Earth's magnetosphere, it's a nominally a dipole, but really very deformed due to the interactions with the IMF. You end up with the magnetopause, which is kind of where the two meet, and you have a bow shock in front of them, and that in itself is, of course, an entirely very complex region, and something that if you interact with the people at JAM et al., they have a lot of really interesting stuff about that. But then what you get is you have what's called magnetic reconnection happen at the magnetopause, which leads to open field lines in the poles. And because plasma is magnetized, all of this interactions with the ionosphere in this region, it becomes very complex, and so you, by necessity, have this very close interaction between the IMF and the solar wind dynamics and what happens in the ionosphere at high latitudes. Next slide. So this is a rather complex plot of kind of some of the major things that happen in the high latitude region. Because, so what I was just talking about before, these open field lines. These are field lines where reconnection has occurred, so they're actually based back. The end of them is in the solar wind. They're not part of the magnetosphere, versus these closed field lines. The magnetosphere has a lot of very complicated currents that occur in that, and often these currents actually close in the ionosphere. So you have these very large current systems where you kind of have current that go all the way out to the magnetotail, but then come back and close in this rather small region at high latitudes where the ionosphere is very conductive. So there's one of the things you'll hear about a lot about region 1 versus region 2 currents, and these are basically just various ways that the currents from the magnetosphere can close in the ionosphere. Next slide. The other thing that happens is because the plasma is frozen in, you actually get, as your magnetic field lines convect. So back when I was talking about open field lines, so these are magnetic field lines that base back in the sun, and as they kind of, they move across the top of the Earth, or the bottom of the Earth, and then reconnect in the tail and then move back, it drags the plasma effectively with it. And that produces these large-scale convection patterns in the polar region. So if you look at it this way, this is a convection map from the SuperDAR network. Basically, the sun is over here, and you have plasma flow straight across the top of the high-latitude region, and then it returns to the day side. This is called a nominal two-cell convection pattern, and it's one of the simplest you'll come. These can get far more complicated when you have the situation where instead of this strong southward IMF, which causes reconnection kind of on the sun side of the magnetosphere, you have northwards or IMF with a strong Y component, because then your reconnection point effectively moves somewhere else. It's still on the day side, but it can be pretty perturbed to where it is exactly, which causes like 4-cell patterns, really deformed patterns and whatnot. So kind of the interaction between the magnetosphere and the ionosphere, it's really important for the high latitude region, and it's something that often we don't, there is a lot of attention to, but because our fields can be a little bit siloed, you end up with what we call a common joke where when you talk to an ionospheric scientist, the magnetosphere is an excessively complicated driver, and when you talk to a magnetospheric scientist, the ionosphere is an excessively complicated boundary condition. So next slide. So the auroral zone. Now I'm going to talk about some of the just broad scale things that you see. The auroral zone is a region about 60, 70 mlat. This is usually on closed field lines, so it's kind of the very upper edge of closed field lines, and it's characterized by aurora. So large levels of particle precipitation, and it is dynamic. Exactly where it is, it modulates depending on the IMF. So when you have a low solar activity day, you can have a relatively small or narrow auroral zone that's kind of at high latitudes. However, it can expand significantly at high latitude days, or high solar activity days. And this is why if you are at high latitudes, or if you're interested in auroral chasing or something like that, they pay very close attention to the solar wind activity, because that starts to move. So getting from a phenomena that you see mostly in Alaska and the Greenland and Scandinavia to something that maybe you can in fact see at the very highest latitudes of the continental United States. Next slide. Again, aurora is a phenomena that many people have devoted huge amounts of attention in literature, but very roughly speaking, solar wind particles become trapped in the magnetosphere. They bounce back and forth due to the magnetic mirror. However, they can either be accelerated or scattered due to various wave particle interactions into the loss cone. At that point, they can actually precipitate down into the atmosphere at high latitude regions in the auroral zone. They collide with particles are excited, and then release emissions, specific emissions which show up as visual aurora. So every single one of these steps involves a lot of physics and a lot of underlying physics. So it's definitely a very complicated process that produce the really spectacular effects. Next slide. So there's two general types of aurora, roughly speaking. Discrete is 1 to 10 keV electrons, generally thought to be magnetic field aligned electric fields, so parallel electric fields accelerating electrons, and these create structured forms. And then diffuse aurora, which are direct precipitation due to into the loss cone through scattering, slightly higher energy electrons and very little structure. One of the really interesting things about the aurora in terms of the magnetosphere-ionosphere interaction is that these structures, a lot of the structures, they act as a kind of footprint or a fingerprint of interesting things that might be happening in the magnetosphere. So that's one of the cross pollinations you see between those two fields. Next slide. The cusp is a very small but important region. It's only a few degrees MLAT, and it's basically the footprint of the reconnection point. So that leads to fast flows, often really interesting precipitation structures or really interesting particle energy spectra there. And that is basically due to the how reconnection works, and it creates various structures there. So next slide. So this creates fast flows, reverse flow events, which kind of create these kind of very strong shears in the cusp region at the footprint of the ionosphere. Next slide. And then finally, the polar cap is basically polewards of the auroral oval. Again, because the auroral oval expands and contracts, exactly what's the polar cap expands and contracts, but generally 70 to 75 polewards of that. And because of the Dungy cycle, so convection that we talked about earlier, you can have a lot of other dynamics here. You create this environment where you have some very dynamic structuring, very fast flows, very fast movement of plasma. So plasma velocities on the order of a kilometer per second or greater are not uncommon. And it creates a lot of really interesting and complex dynamics that are related to the sun's process. Next slide. So one of the phenomena is polar cap arcs, or theta aurora, or sun-aligned arcs. And these are basically precipitation features that cross the polar cap, roughly aligned with the sun, although there could be deviation from that. And then next slide. And then another big one that you're going to hear about are called polar cap patches. So these are isolated blobs of plasma that travel across the polar cap. So it's something like this. This is incoherent scatter radar data. So that's a density enhancement. And it basically travels with the convection across the polar cap. They're quasi-random in that they kind of come from cutting off bits of plasma, or there's another phenomenon called hot polar cap patches due to precipitation in the polar cap. And then next slide. So this is the last thing I wanted to touch on. Really wrapping this up, at the high latitude region, you have a lot of flows, a lot of fast flows, a lot of densities. That means a lot of density gradients. And all of this comes together to produce an area where plasma instability physics is really important. So what plasma instability physics is when you have gradients or shears, you can create situations that are unstable. So small perturbations will grow and kind of create cascades of structuring into smaller and smaller scales. So you have these, what we call cross-scale coupling between, this could have been a patch, but then as it develops, it kind of gets fragmented and structured. And this is something that you might hear about basically anytime you're in a talk where they're talking about gradients or fast flows and start talking about three-letter acronyms, so GDI, let's see, what is GEI, Farley-Buman, FBI. There's a whole zoo of them, effectively. That's talking about plasma physics. And they're really interesting, or plasma instability physics. They're a really interesting topic because a lot of the traditional work has been linear analysis. So if you write out your plasma physics equations and you put in gradients and linearize them, you can analyze them and come up with linear growth rates. However, that's only valid in the linear regime, and very quickly, this is not at all linear. So that can only be really evaluated using sophisticated numerical models and simulation tools. And those can be quite computationally expensive, but are really an interesting topic of themselves. So that's all I have, but feel free to find me later.
Thank you, Dr. Lamarche. Next, we have our final talk of the lightning round. Dr. Ying will talk about the effects of storms and substorms on the TIM system. Dr. Ying is an assistant professor at University of Alabama in Huntsville. She has a research interest centered around the interaction between the solar wind and the Earth's magnetosphere, ionosphere, and thermosphere. She has studied magnetopause reconnection, plasma convection, auroral dynamics, and thermospheric circulation under various solar wind conditions through a combination of spacecraft and ground-based observations. She earned her PhD degree in 2015 at UCLA and was a Jack Eddy postdoc fellow at the Center for Space Physics at Boston University. Let's welcome Dr. Zhu virtually.
Okay. Hello, everyone. I'm very grateful to be here, although not in person, but hopefully in the future, we can gather and say hello to each other. The topic I'm going to talk about is effects of geomagnetic storms and substorms on TIM system. Let's start with the differences between substorms and storms. There are lots of differences, and I'm only going to cover a few major ones. The first one, the cause. Substorms are usually caused by regular southward IMF, during which energy is transferred from the solar wind into the Earth's main-sphere. Storms, on the other hand, are often driven by prolonged and strong southward IMF, such as during CMEs. The duration of substorm is usually short, 1 to 3 hours, but the duration for storm is fairly long, several days. Substorms are associated with magnetic disturbances occurring primarily at polar regions. Storms are associated with disturbances at both polar and equatorial regions. Substorms are associated with auroras and disturbances in the near-Earth plasma sheet, and the storms are associated with auroras as well, but also the buildup of rain current. Rain current actually is the reason or the cause of the magnetic disturbance.
Excuse us, Dr. Zhou. Yeah,
Yes.
your slides is not advancing.
It is not.
Yes, it's sharing to a different screen. Yeah, now it's working.
Okay, so can we go without the full screen mode? Maybe something
Yes,
is wrong.
yeah, that looks good.
Sorry. So, yep, I was here talking about the differences between substorms and storms. The last difference. So the auroras is so storms are associated with auroras and buildup of rain current, and the rain current is the cause of the disturbances at the equatorial regions. So in this talk, I'm going to talk about effects of substorms and storms on a high latitude ionosphere and high latitude thermosphere, actually specifically the upper thermosphere. I will talk about plasma convection and the plasma density for the high latitude ionosphere, and for the thermosphere, the two parameters I'm going to address is neutral wind and neutral density. Again, these are from the upper thermosphere. So let's start with the storm time ionosphere. I don't really know whether it's a surprise to you, but plasma convection during substorm is not a simple two-cell convection. The figure on the left shows the superposed plasma convection before and after the onset. This red vertical line marks the substorm onset time. The y-axis is latitude relative to the convection reversal boundary. So before the onset and during the growth phase, plasma convection equatorward of this convection reversal boundary gets enhanced in a westward direction. But following the onset, the magnitude of this velocity drastically decreases and the direction rotates equatorward. So this is the change of plasma convection at 22 MLT. And if you are curious about a 2D convection map, that's what's shown on the right. Here, the background color represent the conductivity, and these arrows represent the plasma convection. The suppression of plasma convection seen on the left is represented by this black shaded region, and you can see it actually spends a few hours in MLT in the pre-midnight and around midnight sector. And this suppression of plasma convection occurs within the aurora bulge. So the previous slide shows the large-scale statistical convection pattern, but if you look at the localized and the transient convection, this is what you are going to find. These three cartoons represent the night side plasma convection pattern before the onset, during the onset, and following the onset. So before the onset, an incoming polar cap flow channel triggers reconnection at the distant tail. In the ionosphere, this is going to appear as a flow channel in the polar cap, crosses the aurora polar boundary, entering the night side aurora zone. After that, reconnection produces plasma sheet flow channels that propagates earthward and trigger the onset by bringing in reduced entropy plasma. And in the ionosphere, this is going to appear as the flow channel in the aurora zone, propagates all the way equatorward, reaching the growth phase arc, and causing the initial brightening of the substorm. After the onset, this incoming low entropy plasma expands azimuthally. It expands because the lower energy ions follow the electric field drift towards the dawn, while the higher energy ions magnetic drift towards the dusk. And this causes substorm to expand azimuthally. And in the ionosphere, what you will see is the expansion of the substorm aurora bulge and the development of subs and depths. Moving on to the plasma density during substorms. Substorms can trigger large-scale traveling ionospheric disturbances, LSTIDs, due to the heating and the momentum transfer. And one example is shown on the left. The top three panels are aurora observations as a function of latitude and time. And these three panels are taken at three different longitudes. There are three aurora activations marked by the yellow dotted lines. The first one is a global substorm. The second one are PPIs and streamers. And the third is a more localized substorm. The following three panels are detrended TEC. And what we see here is following the three aurora activations, there are three LSTIDs emerge and propagate equatorward. So these LSTIDs are apparently triggered by these aurora activations, and they transport energy from high latitude to mid and even low latitudes. Okay, now storm. During storms, plasma convection gets enhanced, and one specific structure I'm going to talk about is SUBS, subaurora polarization stream. SUBS is associated with the closure of region 2 field line current and the region 1 field line current in the pre-midnight or on the dusk side, and it is often co-located with the mid-latitude electron density trough. The electric field within SUBS is strong because the conductivity there is low, so you need a strong electric field to satisfy the current continuity equation. It's worth mentioning that SUBS also occur during non-storm time, but it is strong during storms. The middle and the right panel shows the magnetic latitude and the velocity as a function of MLT, and also different geomagnetic activity level. I believe this is DST index. So red means active time. You can see that SUBS shifts to lower latitude and also earlier MLT with increasing geomagnetic activity. And of course, the velocity gets enhanced as well. So the reason why I focus on SAPS is because SAPS is important in redistributing plasma in the MIT system during storm time. So SAPS, for example, is believed to be one of the main mechanisms producing storm-enhanced density called SED. So SED is just a high TEC plume near the equator edge of the mid-latitude trough. It is convected sunward. So this is a TEC map. This red tons sticking out from the dayside mid-latitude is SED. SED is not just an ionosphere signature, but it has its magnetospheric counterpart as a plasmaspheric plume. So the figure on the right shows an image observation of the sunlight scattered by the plasmaspheric helium. And the reason why this SED and the plasmaspheric plume occur at the same time and in conjunction is because ionospheric and the plasmaspheric plasma are both governed by E cross B drift. And during storm time, the convection enhanced and expands and the SAPS occur. So SAPS will transport whatever plasma lies in its way, forming this tail structure. But it does not stop at SED. So SED, or plasma convection, can continue to transport material within SED through the cusp into the polar cap and even to the night side. And so this is what, so if this transport process is continuous, then ton of ionization is going to form. So ton of ionization is just this continuous stream of cold, dense plasma entrained in this global convection. If this transport process is not continuous, for example, due to changes in IMF or reconnection being bursty or some other processes, then the ton of ionization is going to be chopped or segmented into polar cap patches. So patches have a diameter about a few 100-kilometer scale, and some examples measured captured by TEC maps is shown on the right. Okay, so that's about high latitude ionosphere. Let's talk about high latitude upper thermosphere. This slide shows a substorm time neutral winds in upper thermosphere. Let's start with the cartoon on the right. So this cartoon shows the disturbed neutral wind relative to the quiet time before the substorm onset and after the onset. Before the onset, you pretty much see the enhanced wind circulation with westward wind on the pre-midnight and eastward wind on the post-midnight. But after the onset, you see a region with suppressed zonal wind that's shaded in blue. And if you recall, in substorm plasma convection, we also mentioned that there's a region of plasma convection in the pre-midnight and midnight sector. So this suppressed zonal wind actually is simply a consequence of reduced ion drag in that plasma or plasma suppression region or convection suppression region. So this cartoon is reconstructed by organizing optical winds or optical wind measurements at different longitude relative to the onset. And one example made at far west of the onset is shown on the left. So from top to bottom, we have AE, aurora measured by Themis all-sky imagers, and scanning Doppler imager, which has the same principle of Fabry-Perot interferometer. And you can see the winds get enhanced in the westward direction following the onset. So that's correspond to this far west longitude. Then the neutral density during substorm. So here, the neutral density is measured by the CHAMP spacecraft, which was about 450 kilometers in height. And these two panels show the neutral density as a function of latitude for low and mid latitude and for high latitude. The black curve is pre-substorm measurements, and the colored red, green, blue is the 3 passes following the onset. So red is first pass, blue is second pass, green is the 3rd pass following the onset. So let's start with the high latitude. The pre-substorm pass shows a gradual increase in density towards high latitude, but this density increased about 15% following the onset, and it's largest in the first pass of following the onset. At mid and low latitudes, the pre-substorm pass shows a relatively flat distribution, But then the following passes show an equatorward propagation of density enhancement. For example, this red curve shows the equatorward, shows the density enhancement reaching about 40 to 30 degree. And then the blue shows about 20 to 10 degree. And then eventually this density enhancement reached the equator, forming this prominent density bulge. Okay, the storm time neutral wind. Here shows the neutral wind pattern as a function of Kp index, and you can see the wind circulation is strengthened with geomagnetic activity. But different from the plasma convection, which has a two-cell convection pattern, the wind is dominated by this anticyclonic vortex that's only happening on the dusk side, but not on the dawn side. So this dawn-dusk symmetry is due to the Coriolis force and the centrifugal forces. These two forces cancel each other on the dawn, but they act in the same direction, so provide a strong deflection of neutral wind at the dusk. The very last parameter let's talk about is the storm time neutral density. The figure on the left shows the disturbed neutral density as a function of latitude and time. And similar to the substorm, you can see enhanced neutral density at high latitude and it propagates towards low latitude. But different from substorm, I should mention that during substorm, the density enhancement is only seen at the substorm longitude. But here you can see the density enhancement is seen across the world, so at day side and also on the night side. Another density structure during storm time is mass density anomaly in the polar cap. The figure on the right shows density, again measured by CHAMP, and the following panel shows the fuel line currents. Here, this density anomaly is co-located with small-scale fuel line currents, indicating this density anomaly is produced locally, likely due to the heating effect of the fuel line currents. But there are other times when the density is not co-located with fuel line currents, and those density anomalies are probably produced elsewhere, but simply propagate here. Okay, so this is a summary. We touched quite a lot material. But during substorm ionosphere, plasma convection shows weak structured zonal convection within the aurora bulge, and the plasma density shows traveling ionospheric disturbances driven by aurora activations. During storm time ionosphere, plasma convection shows SUPS, and SUPS drives plasma density structures like storm enhanced density, ton-off ionization, polar cap patches. Substorm thermosphere, the neutral winds show a weak zonal winds within the aurora bulge, similar to the plasma convection. The density shows elevated neutral density at midnight, which propagates equatorward, likely in the form of traveling atmospheric disturbances. The storm thermosphere shows winds, enhanced winds with a pronounced vortex at dusk, and the neutral density again show elevated neutral density at all MLT, which propagates equatorward. So that's all, and thank you so much.
Thank you, Dr. Zhou, for the nice talk. Now we are moving to our joint Q&A panel. We have 15 minutes in total, and thank you everyone for asking questions. We will start taking questions with Dr. Gasperini. So the first question for Dr. Gasperini is, how important is the ENSO-QBO solar circle coupling effect with respect to just QBO-ENSO coupling impacts in the atmosphere?
Yeah, I think that's, the importance of, if I understand the question correctly, the solar cycle can have an impact, and also the QBO and ENSO coupling. So decoupling all these effects is very hard, and I think it ought to be done using both models and observations. And the models are particularly useful for understanding the relative contributions of certain effects, but I think we are in the need of further research to really understand that effect.
Thanks for the answer. So next question to you is, how can one study long-term atmosphere variations using ground-based instrument? Still a question to Dr. Gasperini.
Yes. I think one of the aspects for ground-based measurements is that we tend to have, not great latitudinal distribution depending on the location of the ground-based data, and so that challenge, imposes challenges in terms of understanding, for example, different wave components that might be contributing. But in general, what we need is a long-term observational record, that uses a combination of ground-based stations. So a single station may be not very useful, but a combination of them, along with numerical simulation as well as data from satellites, can be very useful.
Yeah, thank you for your answer. So let's move on to questions to Dr. Jones. The first question to Dr. Jones. I'll wait for our moderator to, yeah. So we often hear about the quasi-60 wave in the IT, but you said that the free oscillation in the lower atmosphere is 5 days. How does that frequency change?
Well, that's a complicated one, but basically as I showed, all the normal modes or free oscillations are shifted due to the idea of them propagating through a background atmosphere that have mean winds. The 6-day wave specifically is an interesting one. It's debated a lot in literature, whereas it was first thought to be a Doppler shift of the 5-day wave. And then new research came out that it was actually forced by an instability in the mesosphere and it wasn't a result of Doppler shifting the 5-day wave or the normal mode. And so now I think the prevailing theory is the combination of both, depending upon season and latitude. But the answer is it's not one or the other, right? There's still outstanding questions, especially with the 6-day wave, in terms of whether or not it's a Doppler shift of the 5-day wave or if it's a wave generated sort of locally in the mesosphere.
Yeah, great question, great answer. Our next question would be, does the heating-related propagation have significant hemispherical asymmetric performances during equinoxes?
Okay, I'm going to sort of interpret that question as sort of like the latitudinal structure of the tides associated with their sort of seasonal variability. When do they peak? When do they not peak? One thing I didn't get into is each one of those tidal components can be further broken down into what you'll hear people call Huff modes, which describes the latitudinal structure of the waves. Which Huff modes are important depend on season, depend on obviously what the solar forcing is. And so you do have pronounced variations in the seasonal characteristics of the different waves, what latitudes they peak at, when they're strongest, based upon sort of what the sun is doing. And also, for that matter, what sort of tropospheric forces you're getting from like latent heat release, for example. So I think that answers your question.
Yeah, thank you for your answers.
Okay.
Let's move on to Dr. Wright. The first question to Dr. Wright is, since the gravity wave mainly breaking below the ionosphere altitude, how could that affect the ionosphere TID structure?
That's an interesting one, and there's two possible answers. The first one is that the waves could go through in principle, but that's fairly energetic and favourable because they'll probably hit a critical layer before that. A more likely one, and there's a lot of current research on this, is that it's a multi-stage process. So the waves are propagating up from near-surface sources, they're breaking in the middle atmosphere, that's dumping momentum, shaking the air around, and then that generates more waves that go up, and potentially that happens several times, and eventually the waves do get to the thermospheric system or the ionospheric system where they could do the coupling. So more than one step would probably be the dominant theory, I think, at the moment.
Okay, thank you for the answer. Our next question would be, so when defining, could you bring up the question again? Yeah, how do gravity waves parameterized in models in order to compare with observations?
That again is a tricky one, and the answer is they often aren't. In general, models are tuned quite heavily to reproduce the true atmospheric state. And since gravity waves are one of the largest uncertainties, they tend to be used as a tuning knob up and down to fix the other problems, rather than correctly physically parameterize to get it. So the physics is plausible and it does sort of make sense, but it doesn't often map on very well to the observations. There's not very much similarity between them. And I think there probably should be, but it's hard because if you make the gravity waves better, you then make other things worse, is the trade-off.
Cool, thanks. So let's move on to the questions of Dr. Yamazaki. Dr. Yamazaki will answer questions via Zoom. So the first question is there a physical domain, particular scale size, where the A term versus the U cross B term dominates and vice versa in the ionospheric Ohm's law?
Okay, thank you for the question. I think this is about relative importance of electric field versus U cross B term in the ionospheric Ohm's law. So in my presentation, I focused on the middle and low latitudes. And at middle and low latitudes, the U cross B term is the main driver of the currents, and the electric field plays only a passive role. What I mean by that is the electric field is generated in such a way to maintain the ionospheric currents to be divergence-free. But as you go to high latitudes, the electric fields are those mapped from the magnetosphere, and they are the main driver of the currents. So in a very simplified view, as you go to high latitudes, electric field is the driver, and as you go to equator, the neutral wind is the main driver.
Thank you for your answer. The next question is, in your comparison of electrodynamics versus thermospheric mixing, I was wondering where Joule heating fits into this picture.
Okay, yeah. In the talk, I was highlighting the electrodynamic effects versus thermospheric mixing effect by atmospheric waves in the context of quiet time ionosphere-thermosphere system. But during the geomagnetically active periods, electrodynamics are dominated by the electric field penetration from the polar region, and also Joule heating drives the large-scale motion of the thermosphere, and that has much stronger mixing effect on the thermosphere than atmospheric waves coming from the lower atmosphere. So during the disturbed conditions, it's justified to ignore the atmospheric forcing effect from below.
Yeah, thank you, Dr. Yamazaki, for taking all the questions. Let's move on to Dr. Lamarche. The first question is, how do you think we could bridge the gap between magnetospheric and ionospheric physicists to promote collaborations, knowledge-based sharing?
Hi. So the good news is there's a lot of that does happen already. But one of the things specifically is actually right now this week, the GEM meeting, which is where a lot of the magnetospheric specialists present their work. That's actually happening concurrently, and we're going to have joint sessions this week. I think there are 2 or 3 of them. So if you're interested in hearing what some of the people with a more magnetospheric perspective have, certainly go check those out. The other thing is to just be aware of the interactions, seek out interactions with magnetospheric colleagues. Often, a lot of us do work at the same institutions or similar institutions, so just broaden your expanse, and sometimes, often, for me, the other thing that to be aware of is if you're looking for reviewers for your paper, people to revise it, sometimes look outside your immediate community, especially if you think the paper is important for things like drivers and whatnot.
Thank you for the great answer. Larissa?
To add?
It's a great question. I'm trying to talk to you, not there. Thank you, Lucy. Another part of the answer that every so often we actually organize CEDAR GEM meetings together in the same place at the same time, so we can promote closer collaboration. And this is something that we'll be discussing, and we'll see, depending on the feedback and logistics, if we can actually do it within next year, next 2 years, or next 3 years. But we certainly always keep thinking about it, how to promote collaborations.
Thank you. Let's take another question for Dr. Lamarche. How does one couple magnetospheric studies with neutral atmospheric studies?
So the coupling of the magnetosphere and the neutral atmosphere is a little complicated. I think by necessity you have to account for the fact that the ionosphere is in the middle of those two, because magnetic fields don't impact the neutrals as much, but they certainly impact the ions, and the ions can certainly collide with the neutrals. I know there have been studies that parameterize neutral winds. There's one based on CHAMP data, based on IMF positions. So there is an impact. You should be aware of it. Other than that, yeah, that's a lot of neutral chemistry to be aware of, and kind of just how collisions and interactions based on precipitation or the distribution of particles in the magnetosphere might impact the neutral chemistry would probably be a big thing to consider.
Cool. Thank you for the answer. So we will have finally two other questions to Dr. Zhu. So first question to Dr. Zhu is, what are differences in solar storms impacts versus substorm impacts in the atmosphere? We will hear Dr. Zhu from Zoom.
I assume here the solar storms refer to geomagnetic storms, or are you talking about solar flares or CMEs? But either way, let's start with the storms and the substorms. I think the major difference is the magnitude and also the duration. Because if you think about it, the energy input comes in the form of joule heating and a particle precipitation. So during storms, both are stronger and occupy a larger area. I mean, expand to even more equatorward and last for a few days. But during substorm, it's a lot more localized, a lot weaker, and a lot more transient. But if you are talking about solar storms, one thing that we didn't really talk about is the EUV, elevated EUV, for example, during solar flares. And those can cause ionization on the day side. But yeah, that's not something I cover in the talk, but it's also something very important.
Thank you for the answer. We have, yes, we have another question for Dr. Zhu. What are the processes? I guess I'll take the question from Hanan Wu to Dr. Zhu. How do you compare the relative importance of SAPS convection and local FAC to SED?
One thing I need to apologize is that I'm not sure whether I understand this question, because SAPS also comes with fuel line currents. So I don't really know what the local fuel line currents mean here. But to take a step back, the formation of SED actually is quite complicated. And I might have simplified more to an extent that more than I should. So SAPS is one important process, as we addressed. What SAPS does is essentially it scoops the high density at the day side and entrain it into the two-cell convection forming SED. But besides SAPS, there are other processes that are believed also to be important. One important one is the upward flow. For example, at mid-latitude, the E cross B actually has a projection in height. So when you have anti-sunward flow, that actually can lift the upper thermosphere, the ionosphere. So that gives a high TEC value. And besides convection, there's also precipitation, downward ion flux, and even winds. They can all contribute to the formation of SED. I'm not really sure whether we have a clear understanding of the relative importance of all these parameters. But what I can say is that in simulation, with only electric field included, and that's sufficient to produce SED. So what that, I guess my interpretation of that simulation would be, is like electric field is the most important thing for SED, although other processes can also, of course, either strengthen or weaken let's say, the TEC content within SED.
Yeah, thank you, Dr. Zhou, for the great answers. We will collect the rest of the questions and also as long as the answers in our student newsletter. So now let's take a 15-minute break, and we will see each other back here at 11:15.